So today I want to talk about a very famous sorting algorithm called QUICKSORT. The reason I want to talk about it is because I think it's fundamentally misunderstood. It's probably the most popular sorting algorithm. It's probably literally on every device you own. It's so popular. Like it truly runs so much sorting on any electric device you can think of. But I think it's really misunderstood. I think what happens is a lot of people just think sorting algorithms. They think of popular ones, quicksort, merge sort, things like that, and they just automatically assume the runtime is n log n. Which, by the way, if you're not familiar with that, forgive me, I'm assuming that you have some familiarity with computer science and sorting algorithms, and even quicksort, actually. I hope I'm going to help understand it at a deeper level with this video. So let me go over some precursor knowledge that I think will build up to show how quicksort actually works, what the key detail is with it. So first of all, let me give you this thought example. Let's say I'm in a competition and there's a list of scores here. Like someone got 1, someone got 2, I got 5, the next person got 8, and then 10. Doesn't matter. ... Right? And I'm going to tell you this list of scores is sorted, and lower score is better. So if I got 5, that means I'm third place, right? 2 people were ahead of me. Let me ask you this question. Do you have to know what the scores were of the 2 people ahead of me in order to know that I got third? The answer is no, you don't. You just have to know that there's 2 people. For all you care, these scores could be 100 times better than mine, or they could be barely better than mine. For all you know, if this is Alice and this is Bob, you don't even know if Alice beat Bob or Bob beat Alice. It doesn't matter. For you to know that I got third, you just have to know 2 people were ahead of me, right? So that's the very fundamental key insight for how quicksort works, is that to know the position or rank of any one element in a list, you don't have to know the position or rank of every other element. You just have to know how many were ahead or how many were behind, okay? So this insight naturally leads to another very famous algorithm called QUICKSELECT. I'm not going to go over this too much, but let me just write it down so you all can see. And by the way, QUICKSELECT and QUICKSORT were invented by a very famous computer scientist named Tony Hoare. I would recommend you go ahead and Wikipedia him. So the way QUICKSELECT works is it answers this question given some list of data, and you want to know, like in the previous example, you want to know what was the third smallest element in that list, right? QUICKSELECT tells you that. You give it the list and you say, give me the third smallest. And what it does is it goes by and subdivides that list until it ends up with a subdivision that's only 2 smaller. When you have a subdivision with 2 smaller scores, doesn't matter what those scores are. But when you have a subdivision with 2 smaller, you know that the next one above that is the third one that you're looking for, right? So QUICKSELECT is just like an algorithmic way of answering that question that example I had where I got third place, right? Now, you might see how that could naturally lead into quicksort. I don't actually know the history of what came first. I'm just hypothesizing, but I think this is a natural way of teaching it. The first thing is you don't have to know the order of anything else to know the rank of any one element. And QUICKSELECT is an algorithm for that. Now, quicksort is a sorting algorithm that I'm interested in talking about in this video. Again, I unfortunately have to assume that you kind of know how it works already. You're familiar with computer science and sorting and all that. Here's what gets me is a lot of people, I think, falsely compare it to something like merge sort, probably the second most famous sorting algorithm, which was invented by von Neumann. It's not at all like merge sort, though. Merge sort, the way you can think of merge sort is it recursively subdivides a list basically in halves every time, right? So you will have a logarithmic amount of subdivision operations, or I should say layers of subdivision. And each of those subdivisions, you have to touch every single element. So that's where we get this like big O, n, log, n runtime, right? Merge sort is always n log n. Doesn't matter if the list is already in order. Doesn't matter if it's random. Doesn't matter if it's in reverse order. It's always n log n because it always breaks the list down into subdivisions exactly in half and always touches every element, right? People, I think, then get those kind of confused in their head, and they hear, well, quicksort also has an n log n runtime. And that's where the mistake comes about because they're kind of conflating 2 different things. Quicksort works on a fundamentally different principle than merge sort. quicksort, again, in my opinion, is kind of like saying, hey, what if we did quick select for every possible rank? Not just saying, give me the third rank, but give me first, second, third, fourth, fifth. If we have all of the ranks, we have a sorted list then. So I think that's a key insight to quicksort. Quicksort works based on finding the position of every element in the list. It does not work like subdividing lists and then like doing these comparisons like merge sort. Yeah, I think it's kind of a different way of thinking about the problem, even if the end result is kind of the same. So let me give you an example. I'll give you the example that illustrates how quicksort is different than merge sort. Let's say this is our list. All right, you can already see where I'm going with this probably. So, and let's just assume we're doing a recursive version because it's a little easier to understand. So here's the first depth in my like recursive call stack, okay? And let's say we just do a typical implementation you might do like just as an example, or that you might kind of learn it because it's simple. And in this case, you're always going to pick the first element as a pivot, right? Assuming the data is random or whatever. So just pick the first element. It doesn't matter. It's random. Well, in this case, hey, hold on. The data is not random, right? So when we subdivide this into two lists, and we want to say, okay, let's move greater elements to the left and smaller elements to the right. Okay, well, we have empty set over because nothing's greater than 9, right? And then our list over is 7, 6, 5, right? Same algorithm, pick the first element, subdivide, empty list here, 7, 6, 5. Same thing repeats, right? 6, 5, and so forth. You get the idea. And here's our second layer of recursion, third, fourth, ... right? So if we only pick one pivot for every layer of recursion, and this has 5 elements, we have to go down 5 layers deep. And each of those layers, we have to touch all the remaining elements, right? That's not logarithmic time, right? That's going to be quadratic time, right? Assuming n is the length of the list, right? So that's the worst case. Really, quicksort is n squared in the worst case. So you hear n log n all the time, though, right? So how do you explain that? Let's look at a better example. And let's say this algorithm, in this case, instead of just picking the first element, let's say we always pick the middle element, right? So we can subdivide this 1, 2, and then 4, 5. Notice how we got like a perfect subdivision there, right? And look, and let's do the same thing. Let's say, oh, wait, well, we're going to run out of numbers here, but I think you get the idea, right? Is that we have 1 and then empty set, and we're kind of done, right? And then empty set. So you can see here what the pattern is, and you know, run it yourself to see. At the first layer, we get 1 element, and then we double how many pivots we find in the next, right? And then if I had a bigger list, we'd actually, in this layer, because we have 4 subdivisions, we'd actually have 4 pivots, right? And so in this case, if we always evenly subdivide the list perfectly in half, that is where we get n log n. Because the way you can think about it is that you will only have to go log n layers deep in your recursive call stack. And each of those times are touching every element, right? But that assumes you have these perfect subdivisions, because what quicksort is really doing is every pivot, every layer, you're finding an exponentially higher number of ranks of elements. Every pivot, you're finding the rank of that element. That's what the pivot really is. The pivot element you choose is the element you're choosing to find the rank of. So when you go down every layer, you have to be finding exponentially more, 2, 4, 8, etc. If you're not finding exponentially more, you are getting something less or slower than n log n runtime with quicksort. And that hopefully all makes sense based on those initial details I gave you about how quicksort is really kind of about like finding the rank of any one element, using the idea that knowing the rank, you just have to know how many elements are above or below. But that can go wrong if you can't always get an even subdivision. So the way I always think about quicksort, long story short, is I always think about it is that every layer in your recursive call stack, for it to be n log n, you have to be finding exponentially more pivots. If every pivot is finding the place, the rank of an element, you always want to be finding exponentially more. And if you're finding exponentially more pivots, you have exponentially less elements remaining to find sorted. And so that's how you get n log n. But it's really n log n in this perfect case where you always subdivide the list. So hopefully that all made sense. Hopefully it makes you kind of appreciate maybe differences between quicksort and merge sort or other sorting algorithms. If you found that useful, please comment, like, subscribe. Thanks.